You're longer.
$100 more for this seniority count.
Leg room.
It's my advisor, right?
I'm your advisee.
Yep. Oh, okay.
Madam.
Good to meet you. Well, that will satisfy whatever email you sent out yesterday. That we
Yeah,
get
very
to at
good.
least good. So check. So we should talk about it at some point. Are you going to be on next week?
Yeah.
I did outside.
I've done my own, but I'm something that
Okay, let's get started. I had to stay at home this morning for children-related reasons, and I pulled out my laptop, and there was Graham Promotion being streamed into my home. And it was great. The quality was extremely high. It was just almost like being in the auditorium. Actually, it was a little better because I could have beverage in my living room. Here. But it was quite high quality, and I noticed that a couple hundred people were watching outside of this room, outside somewhere, which is pretty good for a Friday morning.
Streaming video.
Streaming, this is all streaming, but also it turns out that on that site they have the archival versions already sitting there.
Oh, really?
Yeah, so if you go mess around and all, so I want to encourage everybody to send pointers to these videos to your students, to your colleagues and all, and really spread the word around. Of course, the assignments website could do a lot of that, but these are really super high quality presentations. I hope you'll agree. And getting word out about the topic and the availability of these lectures, I think will have a nice impact all by itself, in addition to whatever we're doing now. So we'll make some announcements about when they're actually kind of sitting there in a nice format, but they are already sitting there now. On the weekend you missed a talk, you want to catch up. Okay, let me, keeping with my spirit of not making long-winded introductions, I won't make a long-winded one. Just to say that when I sort of envisaged the talks this week, mostly I started with themes. I wanted to have a talk on matrix concentration. I wanted to have one on optimization, on streaming, etc. So I picked some topics, and then I picked the name of the person who I knew was an expert and a really good lecturer, and I wanted to hear their talk. Those are the three criteria. The next two speakers, it wasn't so much that. It was more that I've read their papers over the years, and I always learned something that was interesting and fascinating, and so I just wanted to hear what they might have to say about this topic. I knew they'd say something interesting. So both Nati and Ravi. So with that set up, Nati, you're on.
Thanks. Okay. Thanks. One thing I found out is that it's much easier to be here for 90 minutes than there. So there's all the adrenaline that comes when you lecture and so on. So please feel free to ask questions, make comments, tell jokes, whatever. The more lively things are, the better off we are. So this talk is indeed quite different in more than one way from all the wonderful lectures we've been hearing during the week. So the subjects that I'm going to be presenting are motivated, as I'll explain in a minute, by, I think, a very fundamental issue in large-scale data analysis. But at the moment, I have no good algorithms to tell you or anything. So it seems to me that what I'm trying to describe is the beginning of some research effort that eventually, I hope, will have a substantial impact on these problems. But at the moment, we're still creating the infrastructure. So let me start with the motivating problem. I don't know if you ever asked yourself why it is that in almost any application of mathematics and computer science to the real world, graphs play such an important role. Well, there are lots of different explanations, but one key point is that there are so many things in the world around us that we're interested in, which are large, complicated systems that are really underlined by pairwise interactions. And when we want to understand such a thing, then a graph is really the ideal thing. So, anything, you name it. It can be molecules interacting in biology. It can be people doing business together, anything. Electrons and photons and anything that you want. This is a very ideal situation. But of course, there are lots of real-life situations where the underlying interaction is not pairwise. There are more things involved. So if I want to go back to molecules, in biology, proteins very often, or more often than not, come in complexes. They really interact in a bunch of them, 5, 7 at a time, even more. And what do we do normally? Well, what's normally done is that we take this set of, I don't know, 7 mutually interacting things, and we replace it by a click. But that's a substitute. It's an ansatz, but not a very good one, because you're really missing much of the contents of the problem. So naturally, if you're exposed to enough modern combinatorics, you'd say, yeah, the right thing to do is appeal to hypergraph theory. But unfortunately, hypergraphs are a much less developed part of combinatorics. I mean, the questions are wonderful, but we simply know much, much less. And so another possibility, I mean, if you don't know what that is, don't worry, you'll find out, is to say, well, geometry tells us a different geometry or topology suggests a different point of view. From a topologist's point of view, a graph is a one-dimensional simplicial complex. Again, if you don't know what that is, don't worry. You'll know by the end of these lectures. You'll know. And so perhaps, and that's a possibility, when we want to understand interactions between many things together, we have to appeal to the theory of higher-dimensional simplicial complexes. So my second part so there are going to be 2 lectures. The one after lunch is going to concentrate on higher-dimensional, the combinatorial theory of higher-dimensional simplicial complexes. But having realized this, I started thinking about essentially each of the basic combinatorial constructs that we use all around us. And since one of my main themes in research is to view combinatorial objects from geometric perspective, dimension is a very natural thing to look at. And when I started looking at these things, I realized that essentially all these things, if you look at them properly, are one-dimensional. And they tend to have very interesting higher-dimensional analogs. So the case with the graphs versus higher-dimensional simplicial complexes is just one of many. And it seems to me that in the same way that we are using combinatorics in the analysis of large data, again, left and right, when we want to start develop a theory or algorithms that deal with many-sided interactions, this is the kind of combinatorics that we will need. So what I'm going to be talking about in this lecture is about higher dimensional permutations. And essentially everything new that I'm telling you today is joint work with my student, Luria. Okay, so how is a permutation? So now I have to make good on these general comments that I made. So how is a permutation a one-dimensional object? And how should we think of higher dimensional permutations? What are they? And what would you like to know, etc. So, of course, a permutation is something that can be represented and can be thought of very efficiently and in a very fruitful way in several ways. In fact, one of the things that make them so interesting and important is the fact that they can be viewed from different angles and how to connect these things. But here's one possibility. A permutation is also a permutation matrix. It's the same. These two things are synonyms. So I'm leaving here very cleverly a gap, which I will fill in a second. A permutation is, okay, so I want to say a permutation matrix. Let's spell it out. Is n by n array of zeros and ones such that every line contains exactly one. Right? That's how we think about a permutation. It's just a 0-1 matrix. Every row contains a 1, exactly 1. Every column contains a 1, exactly 1. And the line, we call them 2 different names. These kind of lines we call rows. These kind of lines we call columns. Okay, so let me say here a one-dimensional permutation. And it's obvious where you want to go, right? So if I want a 2-dimensional permutation, I'll do this. I want a three-dimensional permutation. I'll do this. Same thing. So it's a definition, you know. Is it interesting? Is it fruitful? Let's start and see. But beforehand, I mean, what kind of questions do we want to ask? You know, what are the basic things? We know a lot about permutations, right? You can say in some way that all finite group theory, I mean, this is in fact the way, you know, the ancient people in group theory thought about is a permutation group, but they're really all around us. So let's start with just perhaps the simplest things. So the first question about which I'll have quite a bit to say, and the second about which I'll mostly have questions. How many? Question 2. What do they typically look like? So, I don't know if you know this, but if you don't, then it's really something worthwhile knowing. We understand random permutations completely, I mean, perfectly well, and roughly speaking, a typical random permutation has roughly one cycle of length, a half n, then a quarter n, and so on. This is understood perfectly. So it makes perfect sense, and this has been studied a lot, to understand random permutations. And once we know what these are and we get some handle on them, we can also ask this question. But as I say, about this I have something to tell you. About this I mostly have questions. So I think this is a fascinating area of research about which at the moment we know very little. Okay, so let's start. And you'll see that in most cases, you already get everything that's new and exciting, or much of it, just as you go up from 1 to 2 dimensions. Sometimes there are phenomena, or conceivably, perhaps we still don't know, completely new things when you go up from 2 to 3. In topology, such things are well known, that such phenomena, but most of the real story will happen as much of what is going on here. We will see. And by the way, one general comment, I'm not going to take you through any really difficult and complicated proofs. What I'll try to do is, when we get to interesting proofs along the way, I'll try to pull out something nice from the proof, give you a taste of it. So, best moments so you can enjoy and not have to work too hard. Okay, so let's try to understand what is a two-dimensional permutation. So the definition is very clear. You have an n by n by n box. Each entry contains a 0 or a 1. And now there are three types of lines. There is rows and columns, as we used to. And there is what we call, with 2, as we discussed, shafts. That's another type of... and you can, that's a question that makes perfect sense. How many are these objects? But then there is a very simple observation that this is almost as far as possible from being a new object. I mean, in fact, this is an object that mathematicians have studied for hundreds of years. If only you look at this correctly. Why? Because there is a different way of describing this object by means of a topographical map. A topographical map means that I take an n by n array. I'm sitting here, or I'm standing here, and I'm looking up. In the shaft above my head, there sits a unique one. And I'll write the height at which I see it. So what do I get? I get an array, an n by n array. The entries are between 1 and n. And if you think about it for 2 minutes, you see that this condition translates to the fact that every integer k appears exactly once in every row and every column. So a Latin square, that's the name of this. Please don't hesitate. If you have anything to say, don't wait and just say it. So a Latin square is an n by n array. Entries in 1 to n. Every k once in every line, row, column. And that's really an ancient object. I didn't really dive into the history, but Euler had some very important contributions on this, and already in Euler's time it wasn't a new thing. Great. So if this is what I want, then let's look at the literature. Such a classical object must have been studied. In fact, people have thought about this problem for many years. And there was a very nice surprise when I started going over the literature. You know, I was, you can tell, you know, when you have some few minutes time, see what happened. I couldn't find it. I couldn't find, so the reference to the problem were, what's the best known result? And there is a wonderful combinatorics book which I often use in teaching by Van Lint and Wilson. So in my despair, I opened that book. And lo and behold, the best result that I could find is there. So you could ask yourself, such a major problem, how come the only place you find it is in a textbook? Does that make sense? So you'll see in a minute how this happened. I mean, if these two guys actually proved it, why didn't they publish, you know, in a very highly regarded math journal? And the answer is that this is actually a very simple consequence of two deep results. But the derivation is just a few lines. So presumably that was the motivation. So it's perhaps such a thing you want to publish in a textbook and not... So what's the answer? The answer is that Ln, the number of n by n Latin squares, is this. This I must, some drama I must create, right? That's my role as your entertainer. You'll see in a minute why this is blue. Okay, that's the answer. We'll be back to this in a minute. But coming from where I came, you know, when I saw this, I really got the shivers. Because we all know, right? Stirling's formula tells you what happens in one dimension. Well, I write it in a slightly non-conventional way, but this is what you see. So, conjecture in the dimension. This is the most obvious thing to conjecture. Okay, so theorem, this is with Surloi. We are able to prove this as an upper bound. And we have excuses why we can't prove the lower bound. For that, we have a proof and an excuse. Or in other words, there is a challenge there that I think is extremely interesting, but we'll get to that. Okay, so first let me tell you about how Van Lint and Wilson proved the result. It's really a beautiful result which answers really a centuries-old problem. Okay, so for this I have to take you to permanence. Okay, so let me recall the notion of a permanent. So a permanent is you know, a cheap but actually expensive version of the determinant. It's the same as the determinant without the signs. So a permanent of a matrix A is the sum n by n, so it's the sum of all n order n permutations, the product I going from 1 to n, ai pi of I. In determinant there is a sign of pi here you don't have it. Okay, so I think, it seems to me I'm not telling anything new to anyone here. This is a classical object. The computational complexity of this has been a major challenge. There are approximation schemes. This is a wonderful subject in itself that I don't want to get into. The computational aspects of the permanent, really fascinating. Still, not everything is understood, but I don't want to get into this. But being such a natural on the one hand and mysterious object on the other hand, it's really interesting to get at least some estimates for this. And in fact, so there are two major theorems about the permanence, which when put together give you the Van Lint-Wilson result. So let me tell you what these results are. And let me just, so then I will describe to you in general terms I'll give you some of the interesting points from my work with Tzu on how this inequality is proved. And this is motivated by proof of one of these things. So lower bounds and an upper bound. So you have to you have to assume something. So the one result, the lower bound, is the van der Waals conjecture. This conjecture was open for about 60 years. It was finally, this is from the 20s, this is early 80s, I think. Oh, but okay, so we're talking about lower bound. So let us say that A is called doubly stochastic. If all the entries are non-negative, the row sums are 1 and the column sums are 1. So for all I, sum over j of aij is 1, and for all j, sum over I of aij is 1. So one thing to observe is that if A is doubly stochastic, that's an easy fact. But let's even discuss this for a moment. If A, so let us denote the set of all doubly stochastic n by n matrices by omega of n. Okay. So an easy fact, but we'll discuss it for a moment, that if A is doubly stochastic, then its permanent is positive. Of course, it's non-negative. You're only summing non-negative terms, but in fact, it's positive. Okay. And this is an easy consequence of the marriage theorem. Okay, because for this, I don't really care what the numbers are. I just care about the support of A, where it's positive and where it's 0. And what this says is you can find at least one permutation for which all these terms are positive. Now, there is a simple correspondence, which is one of the things that makes this whole thing interesting. You can create, from the matrix, you can associate with it a bipartite graph where this side is the rows, this side is the columns, and there is an edge here between I and J if the Ij entry is positive. And actually, so what this is telling you is that if this graph comes from a doubly stochastic matrix, then this graph is a perfect matching. So it's a very easy consequence of the marriage theorem.
Does it also follow from the fact that the doubly stochastic matrix uses a convex hull of permutations?
Okay, very good.
Trying to do that a little bit.
No, great. This is almost like planted, like magicians who plant somebody. You ask, yes. Great question. Okay, so good. So we will get to this. There is a very important, and I hope to get to this, the Birkhoff-von Neumann theorem, which is, again, not hard. If you know the marriage theorem, you can prove it for yourself very easily, says that omega n is the convex hull of permutation matrices. And from this, again, this follows quite easily. And then, now there comes something very natural. Omega n, then, is just a polytope. It's a compact set. The permanent is a continuous function. It's positive on it, so it takes a minimum. Where is the minimum? So if you never saw this and you'll think about it for 5 minutes, I'm sure you'll come up with the right conjecture. And this is exactly what van der Waals asked. Is it true? So the most natural thing is to take the most symmetric object, namely the matrix, all of whose entries are 1 over n. And this is indeed the theorem. So it took, as I said, 60 years or so. Again, a wonderful subject worthy of a lecture in itself, but this is not what we're doing now. So the upshot of this is if A is doubly stochastic, then the permanent of A is at least the permanence of this matrix for all entries, which is obviously n factorial over n to the n. Okay, so this is one fact that we need. That's in terms of lower bounds on the permanent of matrices. Now we want an upper bound. Again, we need something. What we're going to ask and what we're going to assume. So here, there was a conjecture by Mintz, which was proved. That didn't take so long. I don't remember, perhaps about 10 years. This is from the 70s, Bregman's theorem. And now we're dealing just with 0-1 matrices. 0-1 matrices, the permanent is just a matter of counting perfect matchings. And let's say, so let A, n by n, be a 0-1 matrix. R1 through Rn are the row sums. So the ith row has exactly Ri ones in it, and now we're seeking an upper bound. So the permanent of A is at most the product of Ri factorial to the 1 over Ri. Okay. So where is this coming from? Why should we think that something of this sort should be true? Because take a matrix that is a block sum of, let's say, an A by A block and then a B by B block. These are ones. Everything else is 0. And if you check it, you see that for such a matrix, this holds with equality. By the way, a curious thing that I don't, again, I'm really tempted in so many places here to take a sidewalk, but then we won't do the main things that I wanted to do today. One thing that I keep coming back to, and I still don't have an answer, there is something very curious about this result. You know, of course, if I transpose, then the R's becomes the column sums. So the same thing holds with the column sums. And in general, they don't give the same bound. Is there something that takes into account both the row sums and the column sums? I don't know. But if you have some ideas about this, let me know. I find this very intriguing. Okay. Good. So we have these things. What does it have to do? This is all very nice. I mean, it seems like at the moment I started telling you one story, and then I shifted to tell you another story. Hopefully nice stories, but it's not so clear perhaps how the two are even connected to each other. But now let me tie these things together. So now that we know the Feldman-Gorychev theorem and the Bregman theorem, how can we get to here? So think again of this three-dimensional array. If you think about it, when you take a slice in this, and all these things are really very simple, so I don't even take time to convince you that if you take a slice in this, in any direction, I mean parallel to the axis planes, then what you see is a permutation matrix. It's very easy to check. So let us try. It sounds very naive, but let's try to get an estimate for this layer by layer. So in the first layer, it's clear that we have n factorial. You know, if the bottom layer, there are n factorial choices. So let's see what happens. Let's suppose that we've already covered the first. So these are n by n, and we've created already k layers.
Sorry, Nati, a quick remark.
Sure.
What you just said already implies n over e to the n squared.
That's right.
You're aiming for n over. Okay.
That's right.
Squared.
That's right. That's right. You're right. But it will take just 2 more seconds, and we'll get to the right thing. So how many choices do I have for the next layer? So let's think about it. What I'm looking for is a permutation matrix, an n by n, in the usual sense of the word. But which permutations are okay? I'm allowed in the next layer to put a 1 here, if and only if there is no 1 below me, right? So in other words, what I do from this is I derive from this the matrix B, which is n by n of a 0, and the ij entry is 1 if there is no 1 below it. If I've never used 1 in any of if this partial shaft is still completely free. And then how many choices do I have? Any permutation inside B would do. So the number of choices for my next step is exactly the permanent of B. But you could say, okay, very good, but it depends what choices you made in the previous layer. There are at least...
Is B the slice? I'm sorry.
Is the slice that you're about to construct.
Oh, it's the next one.
The next one, what is possible for the next layer? You already created K layers and now you're going for the next one. So that's how many choices. So there are at least two obvious objections that you can raise. One, that's fine, but what do I know about this B? I could have made here various choices, and these different choices would give me a different B. So that's one of the amazing things about these two, the upper and the lower bounds on the permanent of B that we can derive from these two theorems are sufficiently close together that eventually they will give us this. So they're pretty tight. It's pretty amazing, but they're pretty tight. And secondly, you continue and continue, but perhaps at some point you'll get stuck. But it turns out, you can either read it from this or again prove it by, and I'm making this point for something that will come later on, you will not get stuck. Against the marriage theorem proves to you that you will never, please, Mario.
So why do you need the lower bound? Why is not enough the upper? Because you want to upper bound.
No. Now I want to do both.
You want to do both?
Yeah, I'm doing both for the moment, for 2 dimensions. Higher dimensions I will, as I said, for the lower bound I have only an excuse, I don't have a result. But from now on, it's really a very simple thing. So let's just say a word about what happens. The Bregman theorem is right there. You know exactly, in B, every row has exactly n minus k ones in it. And you plug it into Bregman and you get an upper bound. And for this you have to do a little exercise. This is every row and every column here has n minus k ones in it. You divide by n minus k, you get a permanent, but multiplying this is just a factor to the end that you get. It's all very simple. You plug it in, and it's really 2 lines, and that's exactly the observation of Van Lint and Wilson. And voila, okay. Great. So, how am I doing this time? Okay, I'm doing fine. Okay, so what do I want to do next? Perhaps let's do one more thing that's relatively. So I'll leave this to later. The main thing that I want to do. So what is coming up? The main thing that I want to do is I want to explain to you how we prove this. Bregman's theorem, Bregman's proof was a little mysterious, and again, it's a fairly fundamental thing. So combinatorialists came back to this and gave different proofs and different interpretation. In particular, 2 people who did a lot for us to understand this were Lex Schreiber and J. Kumar Radhakrishnan. And so what I'm going to So actually what I'm honestly going to do here is I'm going to show you in almost full detail Radhakrishnan's version of this proof. So, exactly giving the credit there is difficult. But for me, the moment we understood his version of the proof, this was a moment of revelation for us. And from there on, we really understood what we have to do. So what I'll do is I'll give you Radhakrishnan's proof of Bregman's theorem, and I will explain, I will present it in such a way that it's clear, what further work we had to do, but that I will not do. And what I want to discuss next is about this, higher dimensional analogs of this. But Mario, please.
Yeah, I just wanted to say that if you could generalize the notion of permanent to higher dimension, and you could generalize that theorem,
Yes.
then you would be done.
This is exactly That's exactly the route we take. Exactly the route we take. Yeah, perfect. This is precisely what we do, and I'll explain. So, I mean, these proofs existed in the literature, and you just had to find out which proof really, you know, is such that you can really pull it to higher dimension. That's true. Please.
I was just going to ask, do you know if there's a probabilistic proof of the number of Latin squares? Because there's a probabilistic proof of Bregman's theorem. Or I guess
This is that's the proof. No. So I don't think that you're talking. I may be surprised, but I don't think we're talking about. There is a very strong probabilistic ingredient in these proofs, which I'll present. So I think we're talking about the same proof. Okay, but let's talk for a moment. Let's talk for a moment about this and the lower bound. Why is it, or you know, what's missing in order to prove the complementary? The trouble is, yeah, please.
I think I'm missing something that
Please.
everyone understands. So I see trivially how ln can be upper bounded by n over e to the n squared, and
Right.
now I want to understand how I can get the e squared.
Yes.
And it seems like you are using Bregman's theorem
Yes.
to get the e squared.
Right.
How do you do it?
I mean, I don't. It's really a simple calculation, which I don't want to do. I mean, but all you need to do is ask yourself what happens if all these r's are equal, and you plug it in, and you use Stirling, and that's it. Really, nothing more than that. It's really a two-line calculation. I don't want to do this. If you want, we can spend 2 minutes in the break, and I'll do it for you. You know. I promise you no more than 2 minutes. You and I will do this, and so. But I don't want to get into this. But it's really an exercise. It's not anything beyond an exercise. And I suspect that not everyone in the audience saw this right off. But that's.
But it critically follows from this last observation that this B matrix, the permanent of that B matrix is the number of choices at the next.
Right. That's the critical. And the small miracle that we have here is that the lower and the upper bounds for such matrices are so close, which is.
Scale it down by dividing
Yeah.
3 by.
Yeah, that's for using the lower bound. Okay, but I don't know. But Dick certainly remembers. There was a kind of a Bible when I started doing computer science, which was Gary and Johnson's book on their books, you know, the younger ones. There was such a thing. You opened this paper written. There was this book that every computer scientist had on his shelf or under his pillow or whatever. And the whole subject was new, you know. You can imagine there was such a time. And they were discussing in the book the philosophy and the basic things, and they say, why would you want to read this book? Well, you work for some company, they gave you something, you realize it's NP hard, your boss doesn't know what NP hard is, what are you going to do? And then there is this little cartoon there of the guy standing in front of his boss, and there is a whole line of people behind him, and he says, I can't do it, but all these clever people, they can't do it either. So that's the kind of excuse that we have here. So really this method of getting the lower bound for the number of Latin squares that's based on van der Waals theorem won't work for higher dimensions. So please.
I mean, maybe a quick answer to that question. I mean, Ri factorial to the 1 over Ri has a 1 over E built in. If you just do Stirling.
Yeah,
so
just
you
do
get a 1
Stirling.
over E to the n each step. There are n steps. You get E to the n squared, right?
It's really
In addition to the other E. I mean, this is very rough.
2 minutes, I promise you. No more. Okay, good. So let's talk about van der Waals. And now here is my excuse to why we can't. So let's go to 1 dimension higher, and then I'll be able to also tell you about. Yeah, I think I remember these matrices by. So my title now is that there is no van der Waals theorem in higher dimensions. So even before, great. This is still here. So the point is, let me start in fact from this perspective. You can now, many of these things you can pull to higher dimension. In the same way that there is a bistochastic matrix, you can speak about, let's, 3-stochastic array. It's an n by n array, non-negative numbers. Every line sums to 1. In fact, people in certain kinds of statistics and combinatorial algebraic statistics problems discuss these things to great depth, not just phi, but in general. And it's again a polytope. And you could ask, is there a theorem like this? Is there a theorem like this there? It's true that a Latin square, so let's denote it by omega 3 of n, omega 2 perhaps if I want to be consistent with myself. So it's true that each Latin square is a vertex of omega n. So that part of this Birkhoff-von Neumann theorem holds, but does it go the other way around? So far from it. So what we prove again with Zur-Luria, the number of vertices of this polytope is at least ln to the 3/2. So it's substantially larger. And presumably, I mean, you can't write here that we know anything bigger than 3, but perhaps that's more or less the truth. So so how do we do this? How do we prove this theorem? We prove this theorem by exhibiting other vertices of this polytope, which are not Latin squares. So let me give you the.
Sorry, one quick remark.
Sure.
Had it been true,
yes,
then you would have 3D matching would have been polytime, which we know is empty.
Right. You are absolutely right. Of course, the complexity aspect of this is just what you said. So I'm describing to you now a tristochastic array. Okay. This is a tristochastic array. It's a 3 by 3 by 3 array. Every line here adds to 1. In other words, each one of those is a bistochastic matrix, and if you add them all up, you get the on-ones matrix. That's a way to check it. But I'm claiming that this is a vertex of omega 3, of the order 3 tristochastic, the polytope of y. Because let's suppose that we want to express this thing. There's a little calculation again, which I will not do, but you can check for yourself in even less than 2 minutes. Let's suppose that this is not a vertex. So it's a convex combination of two such objects, of two distinct such objects. And so it's very easy to convince yourself that, I want to express this as lambda times p plus 1 minus lambda times q, where p and q are again tristochastic arrays. If you think about it for a second, then the zeros and the ones that appear here also have to appear in p and q. There is no way around them. And so in every place like this, one is going to be a little above 1/2 and one is going to be below 1/2. So now let me construct, but you see, if this is going a little above, let's say in P. Let's say in P this entry is a little above 1/2. Then this has to, let's say, plus epsilon. Then this has to be a minus epsilon. And this is in P. And something like this in Q. But in the same way, I've almost written a proof. Then this has to be a minus. And what I'm looking for is a bicoloring of some graph here. And this graph contains an odd cycle. That's basically it. So a bit more formally, create a graph whose vertices are all the half entries here. Two guys are adjacent if they reside in the same row, column, or shaft. And this graph is not bipartite. That's it. So this basic, very simple, we do much more complicated things, but but this basic logic is there. Okay, so now let me come back. So see what happens here. Let me come back to, so a very simple consequence. In fact, this is not exactly what we do, but let's not worry about that. In our examples, there are just zeros and halves, but that's not important. The concept you understand. But van der Waalen fails in a really bad way as you go up in dimension, because you see one of the simplest consequences of the marriage theorem is that if you have a regular bipartite graph, then it has a perfect matching. And so this example is not there, but you see the spirit. There is a very simple example of 4 by 4 by 4 thing with 1/2 and zeros everywhere, which doesn't contain, so now I'm coming to whose support doesn't contain a two-dimensional permutation. Okay? So this means that the analog, the two-dimensional analog of this even simple consequence of the marriage theorem is no longer true. Which means that if you want to get a lower bound on the number of d-dimensional permutation, then we don't have the technology. So in fact, a very interesting challenge would be, it's always easier to prove a theorem that you know is true. I'm not laughing. This is, and sometimes it's a very worthwhile undertaking. I think this is an example. So the challenge is, can you prove this lower bound, the true lower bound on how many two-dimensional permutations or Latin squares there are, in a way that at least has a chance to carry over to higher dimensions. I don't know such a proof. Okay, so I think that's a very interesting challenge, and perhaps not hopelessly difficult, because I don't think that people worked on it very hard, and it's conceivable that it's not too difficult. So, but I don't know how to do this. Okay, good. So now we get into the more serious stuff, and so here is what I'm going to do. I'm going to describe to you. Yeah, that's our challenge. So this is what we're doing now. Okay, and then at the end I will explain to you how. I think by the end you'll understand. I'll tell you how, what further steps we had to do in order to carry this proof over. So it's really a very beautiful proof, which has a lot of additional materials and ideas in it. It's really very, very nice. And the truth is, it's really, people like this expression, the wisdom of the crowd. There is this, the crowd is pretty clever to begin with, but it includes people like Bregman and Schreiber and Radhakrishnan. So it's a good team to work with. But it's really the combined effort of many people trying to understand this. So this is what we are doing now. We are proving Bregman's theorem a la Radhakrishnan. Okay. So here is really, so what we're going to use, and this is one of the main contributions of Radhakrishnan. I find it strange. I'm very friendly with him. Jay Kumar. Let's call him by first name, even though he's not here. Is the role of entropy. So we are so this refers to, we're going to use entropy. In entropy, the uses of entropy in combinatorics are a wonderful subject in itself. Again, pioneered and pushed by many people. Jeff Kahn was a major contributor. It's really a very beautiful. Let me give you the absolutely simplest incarnation of this. But in fact, with the hope that I'm not insulting anyone, let me take 2 minutes and just to review basic things about entropy so that we are all on the same page. So if, let's say, P1 through Pn are non-negative, and the sum is 1, then h of p is minus the sum pi log pi. and I'm also going to speak about if x No problems of measurability or any stuff like this, because everything is going to have a finite range. So if x is a random variable, then the p's are the probabilities of the different values that x takes on. So what is important about entropy? There are a few very simple things. One, h of p is less or equal log n, equality if and only if uniform. And the one important thing, one additional important fact that we need is that if our random variable x is actually a vector, so there is always this intuition, again, I hope I'm not insulting anyone by telling such basic things, that this is the information that you're getting by sampling x, and now you get this information revealed in layers. So in this case, you need also the notion of conditional entropy, which is just what you think it is. And so h of x is the information that you get by seeing the first coordinate plus the information that you get by seeing the second coordinate conditioned on the first one, and so on and so forth. So these are all very simple things. If you don't remember them or you saw them once in the past history, these are all very easy facts. Very fundamental, but very easy facts. How does this even connect to combinatorics? So here comes a really wonderful and simple idea. I mean, it's a kind of very simple idea that when in the right hands, as biologists like to say, can really do miracles, or with the right brain or whatever parts of your body you're using to do mathematics. So there is a set omega, nothing to do with it. It's just a big set. That's very typical. Enumeration, right? Enumeration is there is some set. Usually it's hard to describe. And we're interested in the cardinality of this. We'd like to understand that. That's, of course, a very common challenge in lots of places, certainly in combinatorics, in theoretical computer science, even in practical things. So what's the idea? The idea is, let's create a random variable that is drawn uniformly from omega. Omega is a finite set, large but finite. And then it's completely a triviality that h of x is precisely the log. By the way, my logs are to base 2, or sometimes I'll use, not important. As long as I'm always using the same base, I'm not specifying. That's precisely it. Which means, so I mean, it's an embarrassing simple but really powerful idea, that if I'm able to get estimates for this, I'm able to get estimates on that. And that's the way we understand this proof of Bregman's, a good way of understanding Bregman's proof. So we have the matrix A, omega, so it's a 0-1 matrix, like there. Omega is the set, because I'm going to use the set of generalized diagonals in A. A generalized diagonal in a 0-1 matrix is a choice of one element from each row and one from each column. They're all ones. Okay. So of course, just to make again sure that we're on the same page, the cardinality of this is exactly the permanent of A. So now can we do something like this? So we'd like to understand this number, which is the cardinality of this set. Let's try this strategy. Let's define a random variable that takes values in uniformly among the generalized diagonals of A. And let's see if we can work out the entropy of this random variable. And this suggests something. This suggests that perhaps we work row by row. Okay, so let's do it.
Generalized permanent too, I guess.
Say again?
This is a generalized permanent.
No.
So A is now just a matrix.
A is a 0, 1 matrix. Yeah. I'm sorry. No. It's a good thing that you asked, because just to make sure, this is what we're doing. We're proving this theorem. Okay? And this I'll do really essentially in full detail. I'm giving to you now the proof, it's joint efforts of many, but as presented by Radhakrishnan, of this theorem. This is what we're doing now. Okay. And then I will explain, that comes later, then I will explain how this whole methodology can be extended to higher dimensions. But there I'm going to be much more sketchy, just explain one basic idea. Okay. Good, so how do we go about this? So we have this set of tools. This is very suggestive. I'm going to think of, so again, remember, X is a randomly, uniformly chosen generalized diagonal from A. So I'm going to think of X as a vector where Xi says who was chosen, or who is X's element, one element in row I. Okay. It's, as always in proofs, you first run and you crash into the wall. This is soon going to happen to us. And then you sit there and cry a little bit and find ways around it. And so that's how, the first, we are now, brace yourself, we're going to hit our nose soon. But it will pay. Okay, h of x. H of x1 is h is to given x1. Okay, let's concentrate on this. So what do we know? We are now dealing with row I, and we already know what the choices were. So remember, X is a uniformly chosen generalized diagonal in A. Let me just quick reminder. These are the two things that we need to remember about entropy. Okay. So what do things look like? Here's the matrix A. This is row I. So just for convenience, you remember, I only have one assumption about row I. It has Ri ones in it. So just for convenience, I rearrange the columns so that they're here. And okay. And now, we already know what we have done. Perhaps in this row, we picked up this guy. And there is one special guy here. Let's say this is the one, this blue guy, is what X chose from row I. So I already know what the choices were in previous, and so on and so forth. And now I come to here. So I want to use this thing. What can I say about this term? I can say about this term that it's at most log of Ni, where Ni, so given this information, given that these were the choices that X made in the previous rows, Ni, there are still some places, for example, this is still potentially available. There is nothing selected beforehand. So Ni is the number of, let me call it, available ones in row I. Okay. So this means, remember, this is log of permanent A. So the inequality that we got is that log of permanent A is less than or equal sum over I, the expected value with respect to the choice of X, log of Ni. Yeah, now it's the time that we hit our head against the wall, because what do we know about this Ni? It's a random variable. What do we know about its distribution? We have to do something better. We have to do something more clever, because this doesn't bias anything. So let me just introduce a bit more of, and this is really where this really brilliant idea comes in, which traces back to Bregman, but has been clarified over the years. So let me give, before I do this, no, let me just tell you right away what we're going to do. The additional clever idea is to not, there is nothing sacred about this order of the rows. Of course, it affected very substantially the calculation that we did, but there is nothing sacred about this. So the new idea is let us scan the rows in a random ordering. Sigma. So we do this thing, we write this inequality, but with respect to a random ordering of the rows. So when I average this over the choices of sigma, what I get is, here it's a constant, so the averaging doesn't make any difference. So I get that the log of permanent of A is less than or equal sum over I E of x log of Ni of sigma. This means now how many available ones there are in the ith row if I scan the rows by the order sigma. Yes, Mario.
The Ni is a variable too.
Yes, sure. It's a random variable. It's a random variable. Sure. And this is why I said at the first attempt that, okay, we failed. What do we know about Ni? But this randomization is going to help us do this.
So you somehow have to take the expectation over
Yeah. You're absolutely right. Both of them. Sorry, you're absolutely right. Yeah, sure. But even beforehand, let's just take a look at this and see that we're here getting information about the log of the permanent. So let's take the log here and see what we are aiming. So the statement is the same, of course, as saying that log of permanent A is less than or equal the sum over I, 1 over Ri, log of Ri factorial. Let me write it as log of 1 plus log of 2 plus log of Ri. So this is what we're expecting to be receiving. Okay. So let's now look at this and see if we can really convince ourselves. So the claim is that this is precisely, that this is equal to sum over I is the same thing, exactly this thing. This is what we're aiming at. Now,
Not just less than or equal.
no, but actually it's equal. It would be enough to show less than or equal. It's actually equal. So why? Think about it now. Now this is a metaphor from running. You have this.
Just quick question.
Sure.
The sums are equal, or actually that first term is precisely equal to the sum and
Term by term. This guy is equal to this guy. Okay.
What does it mean? Ni of sigma is not necessarily the ith row. It's the ith row that you visit when you have the ordering sigma, so it's not...
Yeah. So let me be precise. This is the contribution of row I. So I keep the name, the original name, when the rows are scanned in order sigma. Okay? This is what I had meant. Yes?
But quick clarification. So
Please.
If you had scanned this first, NI would have been RI. If you had scanned it last, it would have been 1.
That's
right.
right. Absolutely.
It's a
Yeah.
That's
Good. Yeah. This, for example, yeah, that's very good. If I happen to, if sigma puts I first, then NI equals RI. If it puts it last, then it's necessarily 1. Yeah, that's a good indication, just to make sure that we're thinking about the same thing. But here I want to use my running metaphor. So you see, in each of these columns, so you see where these guys are completely irrelevant for me. They're really out of the game. In this part of the matrix, there are exactly Ri things chosen, Ri places chosen. And it's them with whom, so think of it this way. So these columns, or these positions, correspond to runners. You have Ri runners in a competition, and there is somebody, let's say your friend, who you really care about your friend's position in the run. And what he's going to get, because of this expression with the log, he's going to get, the score is going to be log of 1 if our friend comes in last. It's going to be log of 2 if he's pre-ultimate, pre-last, and so on. It's, in general, it's log of t where he is teeth from the bottom.
Doesn't it matter where the zeros are?
No, absolutely unimportant. But let me just finish this. So now what happens? You have R runners. They come in a different, in all orders, and so his position is uniformly distributed among the places 1 to R, which is exactly what you got here. End of proof. It takes a moment to think, but I find this proof really beautiful, and I can say this, it's not my proof, it's everyone else's, so, okay.
This list you wrote just goes up to Ri, right?
Yes. Right? Okay, so what do we do? So as I said, this I have nothing to do with this. I'm a user. This is not our work. But how do you do this now in higher dimensions? So let's say, so I'll just describe the first term, the first step. This is the most profound idea. What we did is more technical, not. I mean, it's quite challenging, but the profound idea certainly comes from there. So what we do now is, so Ri is again, so the expression first of all becomes a bit more ugly and complicated and so on, but the concept remains the same. So there is an expression that has to do with how many ones. So let's say I pick one direction. Let's say I stay with rows. And there is an inequality more complicated than that, which I don't even want to write out, which looks only at how many ones there are in each row. Okay? Just rows. The same asymmetry we also carry it through. And now we pick an order. So we start doing the same thing, except now we scan the rows layer by layer, and then in each layer the rows come in. And so we pick a random ordering of the layers, and we pick a random ordering in each layer of the rows. Now, what is happening here? What is happening here, what I'm saying now is perfectly okay, right, but you have to do some calculation to convince yourself. This is in fact something that you can do even without calculation. So if I want to keep this metaphor of the running competition, what happens is that here we are sending our runners to 2 competitions. So there is a first competition. Everyone that beat our friend is kicked out of is already, I don't know what you do with them, but you do something to them, you send them elsewhere. And then the same group of remaining people, you let them run again. And the score that our friend gets is the log of his position in the second run. That's in 2 dimensions and so on and so forth. The same thing, in every dimension, there is one more repetition of this running game. That's it. So the calculations become more painful and so on, but you get what you wanted. Okay, so this is as much as I wanted to tell you about this. But now I want to, so at the beginning, yeah, I think I'm doing quite okay with the time. So from now on, it's much more stories and speculations and problems and so on. Now you can really sit back and relax. This was the tough part. But it's really, when you start thinking about this, it really opens an unbelievable array of questions. I mean, it's really, well, it's like at the end of a climb. You now see a whole new territory ahead of you and so much to do. Okay, so let me explain. Please. Oh.
One question about the...
Sure.
So you do the entropy method still for
same thing. So the only, so let me explain again. So what we do, let's say just let's say just to get the upper bound, an alternative proof for the upper bound for the next dimension. So you take the layers at a random ordering, and within each layer you go, or the rows. And again, the score that you give yourself eventually, because is the log of how many, of the n of this, how many available ones there are. Right, exactly. Okay, so this is just repeating this thing twice. But so now I want to explain this big view and what is going on here. So remember at the beginning I said I want to count them, I want to understand what they look like when they're random. This I think is a huge challenge, and I have very little to offer. Let me tell you the one or two things that we know about this, but I think this is really a fascinating problem. So the one result that we have here, so the question, there are many questions of this type, but the one question, let's say first question of this sort that you may want to ask yourself is, what does a random, just this, Latin square look like? As I mentioned to you at the beginning, random permutation, we understand very well what a random permutation looks like. These things are understood in fantastic detail. About this we know very little. So there is a Markov chain due to Matthews and Jacobson, which, so I don't know, some people, Alistair was one of the initial, the first people who studied these things, Markov chain, rapidly mixing Markov chains as main means of counting and enumeration. These people have constructed a Markov chain. I'll explain to you the basic things, whose states are all the n by n Latin squares, and they can prove that their Markov chain is connected, but we don't know whether or not it's rapidly mixing. What's the idea? So this is in fact a concept that has been around for a long time. I think much of the insight was gained in fact in trying to get approximate algorithms for computing the permanent, that if you want to do something like this, it's a good idea to work not just with the objects themselves, but also with slight perturbations of them. So for example, in the permanent, one important lesson that people understood relatively early in the game is that although you want to enumerate perfect matchings, it's a good idea to also include in the game the almost perfect matchings and take a rapidly mixing Markov chain, which will spend enough of its time on the perfect matchings, and then you can do all the enumeration. So here, this slightly perturbed version of Latin squares is one where in all places you have one entry from 1 to n. Every row and every column behaves, except there is one entry that is a little different, where you write x plus y minus z. And then every row that doesn't touch this, and every column that doesn't touch it, just contains each of the numbers from 1 to n exactly once. And in this row, z appears twice. I mean, if you count how many x's there are, how many y's, and the z's you subtract off, I'm a little off, I think, here. I'm inaccurate, but it's roughly like this. I think I'm a bit off, but that's roughly the idea. So they created the Markov chain that connects both the Latin squares and these slightly perturbed Markov chains, and they can prove it's connected, but we don't know. So this is I think a major challenge to understand what they look like, and so there are many other really fascinating high dimensional objects here that suggest themselves. So see, for me at least, one of in the next lecture after the break, after lunch break, I'm going to speak a lot about random simplicial complexes, which are the analogs of random graphs. And for me, I think one of the really most fascinating moments in the history of the theory of random graphs was when people around 1980, so Bolobash perhaps is the key figure there, discovered how to sample random regular graphs, which in hindsight is not difficult at all, but this was really an important moment for the field. And so what are regular objects in higher dimension? We understand what a regular graph is. What is a regular object in higher dimension? Here's one, again, a classical thing. So what is a regular graph? Every vertex has the same number of neighbors. So what would be a collection of triples? Now we're talking about a collection of triples. When can you call it regular? So one way is every edge is covered the same number of times, let's say even once. And such a thing is called a Steiner triple system. So it's a collection of triples that covers every pair exactly once. So how is this related how is this related, let's say, to Latin squares and so on? See, a Latin square, a different way of understanding what a Latin square is you can think of a Latin square like this. There are these three coordinates. It's a collection of triples like this. So let's say this is the x-axis, this is the y-axis, and this is the z-axis. So you understand how such a triple represents one of the ones in this three-dimensional array. And what's the property? The property is exactly that every edge here is covered exactly once. So Latin square is the analog of this, the tripartite analog of this. Please, Mario.
So I just started to think to myself that
yes.
There is a first question to this, which is like, how do regular graphs relate to permutations? Because, you know, this is the higher dimensional.
Right.
I could answer to myself that actually permutations have the cycles.
Right.
So actually, it's the two regular graphs, which is just a bunch of cycles, and that's.
Yeah. So the point is.
Higher dimensional of that.
Yeah. So there is now a whole. So let me just point out some of the things here. So you see the analogy between Steiner triple systems and Latin squares. You can also say that the Steiner triple system is a Latin square with a symmetry, where if you have a 1, if A, I, J, K is 1, then A, J, I, K is 1, and so on. There are 6 such conditions. So it's an array with an additional symmetry. And so, for example, can you generate final triple systems at random? So one more thing that Tsur and I did, he already filled the energy levels in the, yeah, you're already exhausted. I'll let you go in 2 minutes. This is what happens when you teach so many years. I always look at the students and I try to discover the moment where they had enough. And and then if I have something funny to say, I'll say this. And if I don't, I'll just let them go. Okay, so let me. Wilson, Richard Wilson, in '74 conjectured that the number of order n Steiner triple systems is 1 plus little o of 1 n over e squared to the n squared over 6. And this 6 and this 6 are, of course, related. So, again, with Tsur-Luria, basically the same technology. The details are completely different, but the basic concept and the basic approach, again, we can prove an upper bound, we can't prove the corresponding lower bound. So that would be an interesting thing to, let me see. Okay, let me just say one last thing. Again, sure, please.
In probability theory, when you study random permutations, it's a cycle structure that
right.
so much is known about.
Right. Yeah.
I just wondered,
yeah, this is what I.
about that. Is that what you're
this is the kind of I don't know. I simply and everyone else in this long line of people, we know nothing of the sort. Yeah, exactly. This is what I said. So it's Poisson distributed. There is. I mean, if
formula.
Yeah, there's. I mean, we really understand. This is a question that is really. By the way, if you never saw these things, there is a very nice description to these things with spaghetti. You have a bowl of spaghetti. Each time you pick 2 free ends and you tie them, and what you get is a random permutation. And the structure of the spaghetti after this, I'm not talking about your hands that are filled with tomato sauce. That's we really understand these things very well, but nothing as you go. And I really think so. Let me just add one more thing, and with this I really finish. Many people are interested in what expanders would be in higher dimension. It's really a fascinating question. And I should say that I think that many of the attempts are going in the wrong direction, because in one dimension we had this miracle that expansion and spectral gap were so closely connected to each other. I don't think that this phenomenon, I think this phenomenon is a one-dimensional miracle, a fantastic miracle. But as you go up in dimension, I think that this is not the right approach. And the right approach should be, it's very easy to explain what expansion is also in higher dimension. And the goal should be that can you find things that expand as well as a random, regular, let's say, 2-dimensional simplicial complex, whatever that means. But to that, in order to even get started on this, we have to understand what these random, regular objects look like. And at the moment, our knowledge there is close to 0. So with this, I stop, and I hope to see you after lunch. Thanks. Okay, it's also okay, yeah, it's also okay to ask questions now if you still have the energy. But
anyone want to ask the last question? We have a little bit of time.
I have a do we have an exact formula for the number of Latin square?
No. Actually, let me just say that I said many times that it's quite miraculous that the lower and the upper bound are so tight. But in fact, this 1 plus little o of 1 is quite a cheat, because this means you only know this thing up to exponential in little o of n squared, which is so even getting these upper and lower bounds closer together is an interesting challenge.
All right, let's solve that over lunch and come back at 2:40.